So I'm Shailendra Kadre, as I said. So today, we'll keep it very light. As you can see, the title of my lecture is Statistics Paradigms. Whatever branch of science we are going to learn, we should be aware what are its major branches, school of thoughts, what you call it, school of thoughts, right? So how it works actually, so how it started, how it works. So if you know all the basics actually, so it's very easy for you to grasp the topic. So I'm starting with very basics, wherein we want to learn the type of statistics, like how many types of statistics, schools of thought, जिसको बोलते हैं ना, main school of thoughts are available in statistics. Okay, so first we'll start with what is statistics. So statistics, I think you must have some. All of you are graduates and postgraduates, so you must have idea of statistics, but it's first lecture, so it's my duty to give you right from scratch. So statistic is the practice or science. So it is C. It's practice or science. Practice means engineering and science means pure science. Okay, so it's practice or science of collecting and analyzing numerical data in large quantities. We collect the data, we analyze the data in large quantities. But analyzing large quantities of data is usually very expensive, and usually that large quantity which we collect, large quantity of data which we collect, that is called population. So usually analyzing entire population is very expensive. Nobody can do that. So what we do small samples we take out of that. We take a small sample out of that, and we apply statistical technique on that small samples, and whatever results we get, based on that we try to find out what are the properties or what are the parameters or what are the characteristics of that population. Based on testing the sample, we found out how the population is. Because population testing is not feasible, so we draw a simple sample, we test the sample, and based on sample, we try to guess how the population behave, what is the characteristics of the population, what is the kind of distribution population is having. So those kind of things we behave, and that's all based on sampling. So what statistics is all about samples. Large population is there, we draw small samples, we study that sample, and from that sample we try to gauge the characteristics of population. That is all statistics, right? So what we study, we want to understand general trends and patterns in a given data set, right? So data is data will have some trends, some patterns. As we go through I'll give you more example, but you can understand that why we analyze the data, to find the general trends in the data. From past data we can see, if we know the trends in we have some data set of 3 Christmas vacations sale in 3 Christmas vacation. So in this particular locality at the time of Christmas, what kind of sale we can expect? Or a website, say Amazon, during the peak sale season during peak sale season in Christmas, what kind of traffic Amazon website can expect? So why Amazon needs that kind of guess or that kind of predictions? Because Amazon is a worldwide website, and if traffic increases by huge amount, suppose traffic increases by 1000%, so their backend resources will not be adequate, right? So for Christmas, they have to deploy extra servers to handle their traffics. Extra server, extra manpower, they have to deploy to handle that extra traffic. So if you can do any kind of prediction for Amazon, that your traffic will be, say you will have around, say 1 billion user in the period of 1 week, like that. If you can predict, then Amazon will be able to deploy the servers, resources, memory, and those kind of manpower. Amazon will be able to deploy. So there are many advantages of knowing future, right, for the business. So that is what general trend and pattern. How can we know that? General trend and patterns we can know that by analyzing the past data, right? Right, I mean, we are doing it in our application also, right? We are analyzing past data and predicting future demand. Right?
Yes,
Why
sir.
we are predicting future demand? We are predicting future demand so that we can do inventory planning well in advance. We
Yes.
should not have shortages. Okay,
Yeah.
so that's why we are doing it. So we analyze trend and patterns from the past data and predict the future so that we can do our business planning well. So all that is our aim of analyzing the data. So we analyze the data, we draw conclusion from it, we do some predictions, and I explained you why we do predictions. So for all these things, we need statistics. And as I told you, analyzing an entire population is not feasible. Entire data of the data set is not possible because Amazon data collection, the kind of data collection Amazon does daily, it may go in petabytes. So analyzing that kind of data is not feasible. So we draw some samples, use statistical techniques on that, and whatever prediction we get on sample, based on that, we try to tell Amazon that yes, your entire population will going to behave like that. Your website traffic, your sale, this particular quantity, this particular product is going to sell this much, this particular product in this region, sale is going to be like this, India sale is going to be like this, US sale is going to be like this. So all that pattern are very important to Amazon to do its business planning, right? So that's where samples are required. Samples are important, and that's where statistics is important, right? So now you might
So
have
one question
learned,
in the previous slide.
yeah,
So in machine learning also we make predictions, right, about the future.
yes.
So what's the difference between the two?
What is the difference between two means what you are comparing with? We are mainly trying to study statistics for data science, right?
Yeah, I mean,
So whatever we are studying is in context with machine learning.
okay.
Yeah, so okay.
Is machine learning is a branch of statistics then?
Yeah, you can say like we are using statistical techniques in machine learning as well, right?
Okay.
We are using basically whatever linear regression, logistic regression, decision trees, whatever you are using. Basically, these are statistical techniques, pure statistical techniques, and we are trying to fit them to our machine learning problems, right? So machine learning is nothing but statistics plus business, like a lot of business knowledge, and we use a lot of business knowledge, and to that we apply a lot of statistics. So combined statistics plus business knowledge becomes your business analytics or machine learning. That's what I would say, right? But still, you are using a lot of statistical techniques in machine learning, right? Without a statistical technique, your machine learning cannot work. Any mathematical technique that you are using in machine learning, its origin is in statistics only, right? So statistics is very important. So next, now if you study like many things you might have studied so far, but nobody might have taught you like how many paradigms are there in statistics, how many schools of thoughts are there in statistics. There are two ways generally statistics is approached. One is frequentist approach, and one is Bayesian approach. See, Bayesian you might have heard, but you might have I'm not sure whether you have heard about frequentist statistics. Anybody has heard, Amit or Jignesh or Anup? Anybody has heard about frequentist and Bayesian statistics?
No,
No,
sir.
sir.
Do you know the
Bayesian,
difference?
But
No.
not heard the term, but probably what I can make out is it's about the occurrence of the items or whatever the numbers in the given.
Okay. Let us see. I will not say right or wrong right now. Let us say what it is. Okay. Let us study what it is. So that's what today's lecture is all about. These are two main schools of thoughts. Some scientists they want to follow frequentist approach, and some scientists they want to follow Bayesian approach. So they are called Bayesian statisticians, Bayesian people, and frequentist people are modern people. Bayesian approach is an older approach. Okay, so both are schools of thoughts, and scientists. There are scientists who follow pure Bayesian. There are scientists who follow pure frequentist. So let us see what is the difference. Okay, so frequentist approach is a modern approach compared to Bayesian approach. So first we'll go for frequentist approach. So frequentist approach to statistics makes predictions. We make predictions based on underlying truth of the experiment, only data using only data from the current experiment. So if we want to make predictions about some experiment, or if you want to make prediction about the data set, we will make prediction only what data tells us. We will not take any prior knowledge. We will not take any prior knowledge into account. Okay. We'll see what data is telling, and that only we'll believe here the future will be. Only based on current data, we'll make our predictions. No prior knowledge will be taken into account. No prior knowledge. Whatever data is telling, that's only I am going to believe that my future will be. Okay. So that's what is frequentist. And frequentist guy is he will believe on only data and experiment. And the frequentist guy will always tell that the experiment should be repeatable, like you learn in physics. Like any physical phenomena which we see is based on experiments, right? Proving you have to prove every theory with the help of experiments. So all these experiments are repeatable. Experiment should be repeatable. So he will collect a lot of data, and he will make some repeatable experiment, and based on that experiment he will predict the future, or he will say whether something is right or wrong. He will not believe any prior knowledge. So that is frequentist. So this is a modern approach. This is modern approach. Okay. Now Bayesian approach people. So Bayesian guys are older guys which used to like this Bayesian statistics. If I'm not wrong, is before 1800 it was invented, like in 1734 or 17 those period only. 1700s only it was invented, Bayesian statistics. So what they believe, they use some kind of prior knowledge, like whatever, suppose you want to prove that Earth is round. They want to prove Earth is round. Okay, suppose you want to prove Earth is round with the help of data. So what Bayesian guy will do? Bayesian guy before Galileo, Europeans used to believe that Earth is not round; it is some other shape. They were not believing Earth is round. Indians were knowing that Earth is round, but European people were not believing Earth is round. So when Galileo saw with his telescope, when Galileo saw some other planets and he saw them as round, then he postulated that Earth is also round, and for that he was punished actually. For telling that Earth is round, though it was correct, those days people were not believing Earth is round, so he was punished for that. He was punished for the right thing. So suppose you are in 1650, or you suppose you are in the year 1550, and you want to believe Earth is round. You are a new scientist. You are a newest scientist during 50. Suppose you are born in 1525, and in 1550, 1560, you want to prove that Earth is round. So what was the prior belief? Earth is not round. Earth is or something square or something else. Earth is not round. So as a Bayesian guy, you will take that prior thing into account. You will believe that first. You will take that into account that Earth is not round, and with the help of some data, then you will either try to prove it or disprove it. But prior knowledge that Earth is not round, prior belief, postulate, prior belief whether they are true or not, they will be taken into account. So in Bayesian statistics, there is always something called prior. Okay. So some prior postulate is there, some prior belief is there, and that belief is combined with current experimental data. And based on both prior and current experimental data, we try to make a conclusion. In frequentist, there is a frequentist, as I told, there is no prior. There is no prior belief. I will not take any prior belief on Earth, whether it is round or square or anything else. I will collect data, and based on only that data, I will prove whether Earth is round or not round. But in Bayesian statistics, I will take some postulate like Earth is not round, Earth is round, and I will collect some experimental data also. So I will combine prior knowledge with experimental data and make some conclusions. So that is the basic difference between Bayesian and frequentist approach. So is it understood? Any questions on this? Anup?
No, sir, no question.
And Jignesh, and have you understood the difference between basic difference between two approaches?
Yes.
Yes.
And Bayesian is much older paradigm compared to frequentist. So as I said, frequentist is a Frequentist is a comparatively modern science. Okay, but in past, you can say 100 years or so, frequentist has originated. Okay, so now we will go in little. Today's our lecture is all about that. What is the difference? So today we will go a little deeper into that. So, like frequentist people believe that they believe the repeatability of the experiment. Like whenever they collect the data from any experiment, they believe the experiment should be repeatable, and they collect a lot of data. They require a lot of data. And frequentists also, they say they believe in probability in long run, and the frequentists people rely on probability in long run and frequency of repeatable experiments. So they rely on data collected from repeatable experiment and probability in long run. Okay. So now, a coin, suppose you take a simple coin. I take a 5 rupee coin or a $1 coin or a 1/4 coin, and I do two experiments. One, I'm throwing the coin up in the air 1 million times. 1 million times means 10 lakh times. 10 lakh. 10 lakh times I'm throwing the coin, and each time when it falls on the ground, I'm noting whether it is head or tail. So 1 million experiments I have done with the same coin. Other experiment I will do, I will throw the coin only 1,000 times. One experiment I throw 1 million times, and in other experiment I throw only 1,000 times. In each experiment, I know whether it is head or tail. So there is a probability, like it has been proven that as the number of experiments grow, in the coin experiment, number of head become number of tails. Like if 50% of the time head appears, 50% of nearly 50% of the time tail will appear. If number of experiments are very large, say 1 million. Okay. So in such a case, coin head will 50% of the time head will appear and 50% will tail will appear. So that is, and once you do 1 million experiment, 1 billion experiment, as you increase number of experiments, the head and tail will become equal. 50% head, 50% tail. But if you do very small experiments, say only 500 times or 1,000 times, you will get a different distribution. Like maybe that 60% of the time you are getting head and 40% of the time you are getting tail. Maybe 70% of the time you are getting head and 30% you are 30% of the time you are getting tail. So it's all about the frequency of experiment and the number of data you have collected. Okay, so if you throw that, you try it. If you try, actually it's very difficult to try a large number of times, but if you try this experiment, fewer number of times, the ratio will be different. Head and tail ratio will be different. And if you throw a very large number, the ratio will be 50-50. So that's how like this frequentist statistic. So any frequentist statistic, like any statistical scientist who believes in frequentist theory. So like if you want to make a theory, how much percentage of head is there and how much percentage of tail is there. Then frequentist guy will tell you, repeat the experiment 1 million times, not 1,000 times. Then only I will make a theory. So as you repeat it 1 million times, then he will make a theory that 50% is head and 50% is tail. He will not believe the data which is coming from only 500 experiments or 1,000 experiments. Okay, so he will not believe in that. So that is the frequentist approach. Okay, and the experiment should be repeated in the same conditions. Experiment should be, see, head and tail, if I have a machine to throw the coin in air, so same machine, same air, same room, it should be done. Okay, under the same condition, it should be repeated. Okay, then see, if there is something which cannot be repeated, then frequentist guys say, I will not touch it. I cannot define the probability. Example, like say 2018 FIFA World Cup. So World Cup season, right? Over. Just now we got over. So 2018 FIFA World Cup, Brazil's probability, somebody says, like if somebody makes some sports scientist or some sports guy says that, very big expert in sports says that Brazil's probability of winning the tournament was 14%. And then he will ask a frequentist guy to prove it. Then he will say, boss, I cannot repeat it. I will not touch this problem. Why? Because 2018 FIFA World Cup can be repeated, can be done only once in 2018. With same player, with same condition, it will not be repeated. So my theory will not work. Okay. So that is how behavior, like frequentist scientists will behave. Experiment which can be repeated and which can be done a lot of time, which can be repeated, then only frequentist guy will come into picture. Like a FIFA World Cup, which can be done only once, he will not touch that for any statistical predictions. That guy will not touch FIFA World Cup because he will say it can be done only once. So it doesn't fall in my theory. Okay. So that's one example. And like you might have heard something like frequentist approach, you might have heard. We'll go through all this. So hypothesis testing you might have learned in your BTech or MTech. Okay, BTech or MTech you might have learned what is hypothesis testing. Okay, we'll do it hypothesis testing towards the end. It is in our syllabus and we'll repeat it. So hypothesis testing, when you do, there is something called confidence interval. So this hypothesis testing and confidence interval are founded on frequentist statistics. Okay, so these are frequentist concepts. Hypothesis testing and confidence interval are frequentist concepts. Okay, and you will ask me a question like, which is better, frequentism is better or Bayesian statistics is better? But there is a lot of debate on that, but there is no agreement and there is no conclusion which one is better. Frequentism is better or Bayesian is better. Okay, now frequentism, like now you might have learned by this time that frequentism has the obvious disadvantage. It needs a lot of data. It needs a lot of traffic volume. It needs a lot of traffic volume. The experiment should be repeated n number of times in the same circumstances. So it needs that kind of data. So like if you want to do A/B testing, like many guys who work with user interfaces and all, we do this. We'll cover this A/B testing and all. Don't worry about it. But like A/B testing means suppose I'll give a simple example. There is a commit button. Commit button is there. So commit button I can place it either at left or at the right. I'm giving a simple example. Commit button on the screen I can place on the left or on the right. So I can conduct a statistical test to decide whether left is better or right is better. Statistical test can be conducted. Like what many people will do. Many people do load it on LinkedIn and say both they will load commit button left on the link. One screen with commit button on left and one screen commit button on right. They will load on LinkedIn. They do it. Many such polls I have seen, and they will ask opinion from the users, which is better. So suppose say 60% or 70% say on the right is better. Then they will put the right on their application. But some more informed guys or more scientific guys, they conduct A/B testing, and HP does A/B testing for their UIs. Which options? Suppose there are two options of putting same thing on a screen on the left or right or center. So HP will conduct A/B test for that. So there is a A/B test of statistical significance which is conducted. So now, like if I want to conduct A/B testing for putting commit button on the left or right, can I repeat it 1,000 times? Can I repeat it 1,000,000 times? I cannot. Right? So in such an approach where repeatability of experiment cannot be done or it is very costly, then in such a case, frequentism is something which is obvious trouble. We cannot collect that kind of data to make any decision with the help of frequentist theory, because it needs repeatable experiments, lot of data. So there are many cases in life, many cases in real life where experiment cannot be repeated. Okay, so in such cases, Bayesian may work better, may work out better. Okay, suppose you have some kind of data which is not very healthy data, some kind of very noisy data or very lot of impurities, data is having a lot of impurities. So in such cases, like Bayesian approach is much better than a frequentist approach, because the Bayesian guy will say, I'll come with some prior knowledge that I learned this kind of making this kind of screen in my prior company. So I have some subjective knowledge of making UIs. You have some data, no? Okay, I'm okay with that data. I'll combine my prior knowledge with limited data you have, and we can arrive at a conclusion. That's what Bayesian guy will say. So sometimes that approach works. So there is a lot of debate going on, and nobody necessarily, you cannot say that frequentism is better or Bayesian is better. See, this lecture might look very dry to you today, but I'm just giving you basics. So don't assume that our lectures or our full course is going to be like this only. Our course is full of numbers and full of solved examples and full of hands-on things. Today it's just like introduction lecture. That's why I'm giving so much of theory and so much of gyan to you guys. Okay. Now, like Bayesian statistics, like Bayesian statistics also works with probability. So like Bayesian statistics also may ask a question like, what is the average male? What is the probability that average male height will be between 60 and 70 inches? What is probability that a person accused of crime is guilty? Means like a person is being tried in the court, and we will tell him he is a murderer, and we are trying him for not guilty. So what is the probability that this person will be guilty? So these kind of questions, both the frequentists will also ask and the Bayesian will also ask. But Bayesian guys, about that person, if Bayesian guys will come, statistician will come, he will tell that yes, this person has a previous crime history. This person has previous crime history. He has done similar crimes in the past also. You will see his history. Like you will see his history, crime history. So it is a probability that the probability is very high that this time also this person might have done crime. But any frequentist guy or any lawyer who believes in frequentist theory will say no. I'll find out evidence only for this case. And if evidence says that he's done the crime, then only I'll say he's guilty. Only based on this, I'll not take his previous history into account. Maybe then in past he has done a couple of crimes. But this time it may or may not be the probability that he has done the crime. So I'll see the evidence only for this experiment. So that is the difference. Okay. So now Bayesian, Bayesian generally talk about distributions, lot of probability distribution. So what is the probability distribution, that also we'll study in future. So like there is a prior, you see the left hand side graph for prior beliefs, like whatever prior belief you have. So that is in the form of a probability. Then you have some evidence that is in a green curve, right hand side green curve, that is evidence. And you combine prior belief and evidence. So like your posterior belief will come. So posterior belief means that is what is the belief, that is what is the conclusion from that statistical test. So he brought his prior knowledge, he took the evidence also, and we combined both. And based on that, whatever belief he draws, that is called posterior beliefs. And for that, for drawing this kind of prior and evidence and all, there is a proper theorem called Bayes theorem. So that also will cover Bayes theorem. And we'll cover numericals based on that, Bayes theorem. Okay. So that Bayes theorem is a very basic and very milestone theory or concept in statistics. So that we are going to cover anyway. Okay. So this is what is Bayesian. And one more pictorial for you to understand Bayesian better. So you have some prior knowledge on the left hand side box. You have some domain prior knowledge, some domain expertise, some subject belief. Like there are many beliefs, right? So some subjective belief is there. Belief may not be true or may not be true. Subjective belief. You may say it's true. I may say it's not true. So subjective belief or domain expertise or prior knowledge here. Then they collect some kind of data based on they combine everything, and then they come up with an updated belief. That data, though your belief is like that, but data is telling something else. So I'm updating my belief. So that is a circle. So if my data is opposite my belief, then I will say no, I will update my belief. So this is a circle actually. So this is a small like a simple diagram for you to understand Bayesian better. So anyway, this PPT I will share with you. So like another majority statement I want to make it here is that, but traditionally in majority of statistical learning, the notion of prior is not used and look favorably. Like, as I said, like if you want to use prior belief or prior knowledge, so that kind of things are not look very favorably. People, many scientists, many statistical guys, they don't want to use any prior knowledge. Okay. Also, computational intricacies of Bayesian learning have prevented it from being a mainstream for more than 200 years. So like whatever I am showing now, prior evidence. So calculation of posterior, it needs a lot of computational effort. It is very complicated. Compute prior and posterior and combining prior beliefs with evidence and coming up with a posterior belief. So these kind of statistical calculations are very complicated compared to frequentist. So that's why Bayesian statistics, though it is existing, it is useful, but it has not come into mainstream. Mainstream in past 200 years. It is in existence for the past 200 years, but it has not become the mainstream. Okay. Now one more concept we are learning now today in what is with Bayesian and frequentist. So like there are two things now. Bayesian will have something called confidence interval. And Bayesian no. Frequentist have something called confidence interval. And Bayesian calls same thing as control interval. Okay. So control interval. So what is confidence interval? So interpretation of 95% confidence. What is confidence interval? How to read a 95% confidence interval? Suppose a frequentist guy comes and say that my confidence interval is 95%. Okay, so how to interpret that? We can be 95% confident that true estimate should lie within lower and upper limit of the interval. Like I can say that like you are asking what is the probability of a person having a height 50 centimeter, I'm just giving a number. What is the probability of height of a person lying between 60 and 70? So like I'll say my height of that person is 65 with a confidence interval of 60 and 70. Like I'm telling you that height is 65%. Height is 65 centimeter, but it can vary between 60 and 70. So I have 95% confidence that true height or true estimate, true height lies between 60 and 70. So that is 95% confidence. So that is who frequentist guy is telling. Now how the Bayesian guy will tell same thing? Bayesian guy will use 95%. There is a 95% that the true unknown means the true height estimate would lie within the interval. He will also say something similar. Okay, there is a 95% probability that true estimate would lie within the interval. Okay, so it is very confusing. Okay, very confusing. I accept it. Leave it. Let us get to next slide. Credible interval is a probability statement about the parameter. Okay, credible interval means Bayesian guy, whenever Bayesian guy tells the 95%, he is claiming about the actual height 50%. So I'm giving you an example. Let us say 50% 50 is the actual number, height of a person 50, and say 65. I'm sorry, I'm confusing. So say 65 is the actual height of a person, and lower limit is 60, upper limit is 70. So lower limit is 60, upper limit is 70, and 65 is the actual height. That's what Bayesian guy is telling. So when Bayesian guy tells that I am 95% confidence So he is telling about the 65. He talks about the 95. He is telling about the 65. That I am 95% confidence that 65 is the height. But when frequentist guy tells about, the frequentist guy will tell about the confidence interval. Frequentist guy will tell same thing about confidence interval. He will talk that I have 95% of confidence. I have 95% of the confidence that the upper limit is 60, lower limit is 60, and upper limit is 70. But the Bayesian guy will tell about the actual parameter. The Bayesian guy will tell that I have 95% probability that true height is 65. But frequentist guy will say, the frequentist guy will not talk about true value. Frequentist guy will talk about the lower limit and the upper limit. So frequentist guy will tell that there is a 90% probability that lower limit is 60 and upper limit is 70. Did you get this difference? I think it's very confusing for the first time.
Sir, I mean, it's like the frequentist will tell that, I mean, the height can be between 65 to 90.
60 to 70, yeah. 60 to
60
70.
to
Let us talk 60
So
to 70.
it's a range, we can say, and for that Bayesian we can say the some specific number.
The Bayesian confidence, see frequentist confidence interval, no. So he will say that I am 95% confident that lower range is 60 and upper range is 70.
Yes.
And Bayesian guy will come and tell you that I am 95% confidence that height is 65.
65, that constant the
Okay.
confidence.
And then apart from that, he is giving two limits also. Like Bayesian also give limits, and frequentist also will give limit. But when Bayesian talks, he will tell that I am 95% confidence that height is 65. And when frequentist will come, he will say frequentist will come and he will tell that I am 95% sure that lower is 60 and higher is 70. Understood, na? So that is the difference between confidence interval and credible interval. Actually, these concepts are not being used right now. I have just introduced it here. And when we'll do hypothesis testing and more concept, these concepts will be made more clear with the help of numerical examples. So that time it will be more clear to you. So right now you just keep two things in mind, that frequentist guy talks about confidence interval and Bayesian guy talks about credible interval. So confidence interval is nothing but frequentist guy will tell you that I am 95% confident that lower limit is 60 and upper limit is 70. That's how frequentist guy will tell. Bayesian guy will come and tell same thing. I am 95% confident that height is 65. That is the difference between Bayesian guy and a frequentist guy. And now clinical guys, like whenever doctor talks, both
will talk about the interval only, right?
No, and Bayesian, both will have interval.
Yeah.
But by whatever percentage, 95% confidence interval, the level of confidence, 95% level of confidence is given. Bayesian is giving that level of confidence to the height 65, and frequentist is giving 95% confidence to the limits. That is the difference.
But here, if you see the first bullet, right, both looks to be same to me.
No, yeah, you come to second. First is very confusing. You come to second.
Okay.
You come to second, yeah. So this is the real difference. That will give you real difference. This is, you read this 3-4 times, then you will understand. Credible interval is a probability statement about the parameter. Credible means whom? Credible means Bayesian guy. Credible interval is a probability statement about the parameter. He will tell, I am 95% confident that height of this person is 65 centimeter. Okay, 65 may be an absurd number for a person, but I'm just giving a number. So credible guy will tell, I am 95% confident that height of this person is 65 centimeter. And the frequentist guy will tell, I am 95% sure that height of this person can lie between the lower limit of the height is 60 and the upper limit is 70. So he will attach confidence level to the limits, frequentist guy. and Bayesian guy will attach the confidence level to the parameter value itself. So that's a basic difference actually. Understood, Anup?
Yes, sir.
Anup, is it clear?
Yes, sir.
Okay, so right now I'm introducing just the concepts here, and we'll elaborate them later on anyway. So, like confidence, whenever they talk about credible interval, so credible interval is always Bayesian guy, and whenever Bayesian guy comes in that interval, problem specific contextual information, some prior knowledge is always included, because you see, you know that Bayesian is always combination of prior and evidence. So whenever we talk about credible interval, in that whenever we talk about credible interval, that means that in that knowledge of prior is included. Contextual information is included in Bayesian credible interval. And confidence interval, when we talk by frequentist approach, he is talking based on only data, current experiment data. He is not taking anything prior into account. Okay. So the clear advantage of using Bayesian credible interval is complexity of computing posterior distributions. So calculation of posterior based on prior and evidence, like here, like calculation of posterior means middle curve based on prior curve and the right hand side evidence curve is very difficult. So Bayesian is not a very preferred paradigm compared to frequentist. Okay, so now everything is the last slide, and everything I think we have understood. So let us summarize it. So frequentist means data is repeatable, random sample, there is a frequency. So frequentist will tell anything. He will tell that it's a random sample. I'll take random sample and experiment should be repeatable. Bayesian guy, same thing. Data is fixed. He will work with less data. And probably he will work with less data. He will work with few sample also, because he is taking the prior knowledge also into account. Bayesian guy. But to do the same thing, frequentist guy will need more data and more number of experiment, and experiment should be repeatable. Next, no expression of beliefs. Like there is no prior expression of belief. There is no prior subjective knowledge required for a frequentist. But prior subjective knowledge or prior hypothesis or prior domain knowledge is required for Bayesian. Now frequentist third point. Provide us with a point estimate using MLE and least square estimates. So like in MLE, I guess it is mean least estimate or something like that. We do when we do optimization. So the concepts of MLE comes. Like it's a least square optimal MLE. Like better Google it. It's something like that only. So. And then maximum likelihood estimation. Maximum likelihood estimation. So these things will take in our future lectures. So maximum likelihood determination, least square estimate. While like Bayesian gives us a posterior distribution, he talks everything in terms of probability distributions. Okay, high density interval with mean mode, and whenever a distribution comes, then you will have mean mode and median and concepts and all that. Parameters are fixed and unknown. Parameters are unknown, random, and described probabilistically. Confidence interval over an infinite sample size taken from the confidence interval over an infinite sample size taken from population. 90% of these contain true population value. Third, I want you to read this one here. Confidence interval. So lot of infinite samples are taken, and 95% of these contain the true population value. Even I have not understood what is it. And credible interval, a 95% probability that the probability value is within the limits of interval. So I think same thing which we have discussed, confidence interval and credible interval, they are talking in a roundabout way. So I'll not stress much on it, and I'll stick to whatever we have discussed. Like whatever we have discussed means these two things. These two things, like credible interval is a probability statement about the parameter. Credible statement is a probability statement. It talks about parameter, and confidence interval talks about the limits. Okay, so that's where I'll stick to it, and I would like to ignore these definitions given here.
If it talks about just one value, then it should not be called as an interval, right?
No, actually, Bayesian, whenever it gives one value, it will not give you any one value. It will give you a complete distribution actually.
No, I mean, if you go back to that slide, yeah, you said credible interval is a probabilistic statement about the parameter, right? So, and then I think what we are saying is it's the 95% probability that the value is say 65, height is 65, right? So
yeah, so when you give a probabilistic
about a value,
yeah,
you're talking about just one value, then I'm sort of confused.
No, actually, we are talking about one value with complete confidence interval, right? So we are in effect, we are giving a complete probability distribution. We are telling that there is a 95% of height being 65 within the interval of 60 and 70. So we are giving a complete distribution here in a statistical means. It's a complete distribution actually.
Okay.
It's not a single number that I am telling. I am giving a complete distribution, posterior distribution here in Bayesian. Okay. And then like p-value, significance level, like I told you, hypothesis testing and like confidence interval, p-value and all these concepts. So they are based on FREQUENTIST and Bayesian factor considered in a direct test or null or alternate hypothesis, yielding in a measure of high strength of evidence. So actually, I would like to ignore last 2, 3. These two I would like to ignore, that like whatever confidence interval definition and statistics. So they are talking in a very roundabout way. So like point number last point number 3 and 4 I would like to ignore, and fourth point is more clear. Less computationally expensive. FREQUENTIST is less computationally expensive, and Bayesian is more computationally expensive. That's why FREQUENTIST is the preferred way, and Bayesian is computationally difficult to compute. Okay. So for confidence interval and credible interval, whatever difference we have studied, I would like to stick to that way. And this point, last but one point, I would like to ignore actually. Actually, I have done a mistake. I would have not included it into the slide itself. But anyway, so it has come now. So let us ignore like point last but one and point before that. So I think these differences are clear. So today was very heavy kind of lecture with a lot of philosophy, lot of theory, and lot of things. But I think if you understand these kind of paradigms behind whatever you are going to study, I think it helps you a lot actually. Like what is the frequentist approach? What is a Bayesian approach? I was puzzled for so many days actually. People used to call Bayesian statistics, Bayesian statistics. So many places it is written Bayesian statistics. Then I used to wonder, were any other types of statistics also existed other than Bayesian? If that, why is it not taught to me? Then when I decided to teach the same subject, then why not start with paradigms, which puzzles me for so many years. So I started with the most basic things of statistics, and now I want to give you a glimpse of what we are going to study. So this is the end of today's lecture. but I want to give you a glimpse of what we are going to study in the syllabus, so that your interest level will be maintained. Otherwise, in the next lecture, you will not come.
It's not like that.
No, it's very heavy today, I know.
Yeah.
So, where is that? I want to show you, the syllabus. So, my statistical course. So, it's my duty to make it as interesting as possible, right? And it will be interesting when I discuss a lot of numerical example and some example. So, I understand that. But today's lecture, there was no choice. Lecture number 0, okay. Okay, so we'll start with variables, events, independent events, mutually exclusive events. Then we'll get into basics of probability, what is discrete continuous probability, joint probability distance, what is central limit theorem. If you are a data scientist, you cannot ignore central limit theorem. Then we'll come to probability laws, what is union, intersection, probability. If two components are in series, what is the probability of failure? Two components in parallel. Then Venn diagrams of probability. Then we'll come to like Bayes theorem. So it's all Bayes theorem. One lecture is on Bayes theorem. So Bayes theorem is very important and basic concept of. So whatever Bayesian statistics we have discussed today is based on Bayes theorem. So we have one lecture on that, and a lot of numericals everywhere. Okay. And then we have a lot of we have two type of probability distribution: discrete and continuous. So in continuous, we are going to take lot of distributions. We are going to take like Poisson, binomial, exponential, uniform, T distribution, distribute student T distribution. Then normal Gaussian, everyone has heard actually. Then right left skewed distribution, cumulative distribution. So whatever distributions you have heard so far in your life, everything we are going to cover. Then we come to statistics. So this is the end of probability here. Here, slide number 7 is the end of probability. So we have a lot of 4 lectures we have totally on this, excluding today's 4 more lectures on probability. Then we come to statistics. We talk about population, sample. Then we talk about estimates, like how to do point interval, point estimate, interval estimate, descriptive statistics, inferential statistics, prescriptive statistics, predictive statistics. These are the type of statistics. Then all these definition, they might be troubling you throughout your career so far. What is mean, median, mode, expected value, in discrete and continuous variable, then covariance, correlation, so many concepts will go. Covariance, correlation, and then correlation coefficient. Lot of these confusing things which are asked in interview, everything will cover. Correlation formula, covariance formula, difference between covariance and correlation. All will be covered with numerical, okay? Then we will give one lecture to very important topic called hypothesis testing. So p-value method and null hypothesis and alternate hypothesis. Okay. So one lecture on this, and last lecture is on. You might have heard a lot of tests actually. They are actually see all these tests. They are troubling me for so many days. So once for all, I covered everything. Set test, T test, paired T test, independent T test, one sample T test, ANOVA, chi-square, parametric test, non-parametric test. So how to, and after that, so many tests we'll discuss. After that, we'll discuss how to choose. For a case, if I have some case and I have to apply a statistical test of significance, how to choose the test. And all this will be covered with numericals, okay? So from now on, get geared up for numericals. I'll share you a mathematics book. I shared you a mathematics book. Who will have some solved example in the class. I'll share you mathematics book. And after doing solved examples, if you want, you can practice at home. And it's a non-coding course, okay? So it's not a coding course. It's a completely non-coding course. But if you practice, it will be forever with you. Okay. So more than this statistics, you don't need in data science, at least for beginning.